So in the previous section, we indicated that it is possible to build complex systems out of neurons. And we saw just sort of a whirlwind set of examples of doing things that involve, well, vision, which fine, everyone's quite used to using neural networks to do vision, but also to remember things over time and to do motor control and to do planning of a sequence of actions, completing a pattern, doing different tasks at different times. And I guess the core question is, okay, I've sort of claimed that it's possible to, and I've shown you the results. How did we go about building those systems? So that's what I want to talk about now. And in particular, the approach that we're going to use is called the Neural Engineering Framework. From this book in 2002. And it basically lays out a general framework for doing computation with neuron-like systems. The particular emphasis in the book is, again, matching onto neurobiological systems. So the neurons there are meant to be more biologically realistic, but all the techniques work for neurons in general and sort of more traditional digital neurons as well. The core idea is to say, all right, well, what is it the neurons are good at? And we take the standard example from all ideas of neural networks is that neural networks are good at function approximation. Okay, so here I've shown a completely traditional three-layer network, one input layer X, a hidden layer in the middle, and then an output Y. And if that input is X, is say has three values, and the output Y has two values, then we can sort of say that, okay, well, if you set the weights to these for all of those connections, then the system as a whole is computing some function, Y is some function of X. So that's the core idea that we're going to go with. There's nothing particularly controversial here. I'm going to introduce some things that might be a little bit weird for people that are used to neural networks. In particular, I'm only going to have a nonlinearity at the hidden layer. So the blue items are traditional neurons. They can be sigmoid neurons, they can be spiking neurons, they can be rectified linear units. Any neural network or any neural nonlinearity can go there. For the green boxes, the input and the output boxes, I'm going to actually say that there's no nonlinearity there whatsoever. And that's going to become important in a little bit, but it doesn't actually affect the being able to think of this as a function approximation. You only actually need the nonlinearity in the hidden layer in order to approximate functions. So X I can just think of as some, say, three-dimensional value. Y is some, so a vector, and then Y is some vector of length 2, and we're doing some mapping between them. I do also want to point out that the representations, if we want to think about what's happening in terms of how information is being represented at different points in the system, the inputs and outputs we can think of as being very localist in terms of there's probably maybe my input is some position, XYZ position of an object, and my output is, say, the angle I need to rotate my head at in order to look at the object. So say that's the function. In the green boxes inside of X, we have one box for each of the three things being represented. On the output Y, we have one box for each of the two things being represented. So those are very localist. Each of those boxes we can say what they represent. In the hidden layer, the blue items, the things that are actually neurons, that value of X is somehow distributed across the activities of those neurons. Right, so this is the traditional distinction between localist representations and distributed representations. Okay, so that's perfectly normal and not a surprise. I'm going to introduce some terminology here. I'm going to call the input weights, I'm going to call them encoders, and I'm going to call the output weights, I'm going to call them decoders. So E for encoder, D for decoder. And the reason to do this is that we're thinking of the encoder E as taking that localist value X and determining how it's distributed across those neurons. So how that information is being represented in those neurons. That's why we call it an encoder. And then the decoder D, the readout weights, so the connection weights that are coming out of the distributed layer, we're going to call those a decoder because what they're doing is they're taking the activity of those neurons and decoding them in some way to get us the value that we want. In this particular case, the value Y. Okay, so that's just terminology. All right, but as far as what we're actually building, this is a totally normal neural network. I'm not going to draw all those internals all the time, so that's exactly the same diagram, just without drawing any of the internals. Good. So, what if I want to build more complex systems out of this? Well, I could just take the output from one and pass it into something else. All right? So I'm just taking the thing that was an output and feeding it into another, feeding it as input to the next group. Okay? Now, if I did that, fine. That would just simply be, well, if there's some function be computed between X and Y, and there's another function be computed between Y and Z, well, now this whole thing is a big giant neural network that computes the combination of those two functions. Right? So there's nothing particularly shocking about that. But I've got something a little bit weird here. This isn't traditionally how people do multiple layer neural networks. In particular, when people do multiple layer neural networks, you don't tend to have this intermediate thing Y that doesn't have a nonlinearity in it and is just sort of I'm basically doing one weight matrix and then another weight matrix immediately afterwards. So the weight matrix D sub A and the weight matrix E sub B, they don't tend to exist in in traditional neural networks. What would happen in a more traditional neural network is there would be one giant connection weight matrix right from A to B, and there wouldn't be this intermediate value Y. So what's up with this? Well, because Y isn't doing anything, we can actually convert back and forth between this representation, where we have this intermediate value Y, where I've specifically said, hey, look, this is the function that I'd like to compute. There's two functions I want to compute. I want to compute the function that takes me from X to Y, and then I want to compute the function that takes me from Y to Z. That's me thinking about it in sort of programming terms, but in terms of neural network terms, I could just do this. Particularly, I could just multiply those two weight matrices together. So again, let me go back there. So D sub A and E sub B, if I just multiply those two weight matrices together, I get a new weight matrix that does exactly the same thing as that separated one. What I'm pointing out here is that we can design in these intermediate variables if they're things that we think need to be computed, or if they're part of us planning out what the functions are that are being computed. But if we want to think about them as a pure neural network, those intermediate values actually disappear. They're not actually represented in the system in any way. However, this actually starts being a situation where we start being hardware dependent. So if you'll notice this, so this particular weight matrix, so if say there was maybe 100 neurons in A and 100 neurons in B, well, that weight matrix is 100 by 100. That's a very big weight matrix. If Y is only, say, 2 dimensions, then that's going to mean that D sub A is a 100 by 2 matrix, and E sub B is a 2 by 100 matrix. And so that's a much smaller amount of memory to store these two separate weight matrices. The other way to think about this is that this weight matrix, WAB, can be factored into these individual components. And those factors, depending on how we want to implement our hardware, it could be much more efficient in terms of memory to implement this hardware in hardware. This is going to be one of the situations that's going to be really important when figuring out, hey, is this, or what is the right way of mapping these systems onto FPGAs? So this ability of pointing out that weight matrices tend to be factored ends up giving us a lot of computational efficiency. Okay. That said, this is just sort of a single set of functions of just going, okay, first I do compute this function, then I compute this other function. We can probably do more complex things than that. And that's exactly what I want to say. So exactly how I build all of these large systems is to say, okay, if you want to build a large complex system out of neurons, really what you're doing is you're saying, well, I'm going to postulate that there's a whole bunch of intermediate variables. These are the green boxes I'm showing here. I'm saying, look, u, v, x, y, z. And then I'm going to say, all right, what are the functions I want computed between these variables? All right, and I can combine these things. I can say, all right, x is some function of u and added to some function of v. I can combine these things in various different ways. Right, this is how I want to express algorithms, and algorithms, once they're expressed in this form, I can then convert into neural networks. In fact, we also can get slightly more power than that. So if you also start including recurrent connections, that turns out to actually give you the ability to compute differential equations. So you can start saying, all right, my individual components are acting somewhat like integrators, and I can have these inputs changing over time. As that means that not only do I have access to building up these large systems using variables and pure functions on those variables, but I can also say, all right, I want particular differential equations on these variables. Yeah. Any system of that form, once I have it in that sort of situation, then what I can do is I can say, all right, let's replace each of those functions with neural networks that are approximating those functions. So this, again, every single one of those connections is a fairly traditional neural network, but organized in a very odd way. I can build each of those individual neural networks on their own, and then I can, once I've connected them up in this way, I can then remove those intermediate variables if I want to, as depending on computational efficiency questions. But in terms of the final neural network, it's going to end up looking like this, even though my initial program ended up being something like this. So that's exactly what I want to do, what I mean by saying that we have sort of a different way of thinking about computation. What I want to do is I want to think about computation as this set of variables, functions, differential equations, all of which I know I can turn into one giant neural network at the end. And importantly, I don't have to train this entire network all at once in the large form. I can actually just individually train the inputs and outputs to each of those blue neuron ovals. I can train those independently as if they were just a tiny little neural network on their own, and then I can combine them all together and get something that will behave how I expect. Of course, it's worth taking a little moment to say, okay, well, how do we get those E and D? So if we zoom in on each of those individual components, this is what I always need to do, is I need to say, well, for any one of those connections, I know what my input is, X, I know what my output is, Y. I know what mapping I want between X and Y, but how do I find those encoders E and the decoders D? So this is the question of how do I get the weights in my weight matrix, or in my neural networks. And there's a bunch of different techniques for this. One that we use fairly often is simply to say, all right, let's randomly generate E, and then solve for the optimal D. This just turns out to be just least squares minimization. If you have some particular function, some particular mapping from X to Y that you want to closely approximate, you can set E randomly, and you can just use least squared minimization to very quickly solve for D. And that means you don't have to worry about training regimes, or you don't have to worry about all the details involved in waiting and hoping for your neural network to learn exactly what it's supposed to do. You can just do this very quickly. This is not going to be the best answer, mostly because we're randomly generating E, but it actually turns out to not be that far off of the best answer. The more common thing that people will want to do is to do this offline, is to do this with backpropagation learning. So this is the standard typical neural network learning rule, where you randomly initialize all your weights and then you gradually adjust the both the decoder weights and the encoder weights based on the error at your output. So based on the difference between what Y currently is and what you want Y to be. So that's backpropagation learning. That's definitely an approach that can do that. And the nice thing is you only have to do backprop on one particular component at a time. Once you've done it to all of them, you then combine everything together and you get your full network. But that's only for situations where you are wanting to make strong claims about what those individual components are. If you want to, you can also do backprop across the whole system, which is sort of the way modern deep networks often work. In modern deep networks, when you want to train across the whole system, that's what you're really saying there, or one way to think about what you're saying there is that you're not making any claims about what those intermediate variables are. You just simply know U, V, and Z, and so try to do learning across the whole system. But if you do have a guess as to what those intermediate values are, if you have knowledge about what the algorithm is that you want the full system to do, then that's when we can say, oh, hey, look, this is the intermediate values I want you to compute, X and Y, inside the network. And that is going to be a much faster learning, or a much faster way of getting those weights. It's also worth pointing out that even if you do have a good idea about what all of the individual steps are in the algorithm that you want to implement, once you've generated that full network, you can then use that as a starting point for deep learning if you want to. And you can just think of this whole system as a way of generating the connection weights for the initial connection weights for a fairly complex neural network, rather than relying on just putting them randomly. That said, this always requires you need to have an idea about what the algorithm is that's being implemented. So that's sort of the key difference between this approach and traditional deep learning, is that we're saying, if I know something about these internal components, let's take advantage of that. Okay, so those are both offline learning rules. It's also worth pointing out that we can do online learning as well. And in particular, any of the standard neural network learning rules can now be applied in this on top of this sort of situation. A really common one that we tend to use is just delta rule, modified slightly in order to take into account for the fact that you want to be able to compute your error signal using another different group of neurons. So that is, instead of having your error signal being some sort of external stimulus, you actually want to be able to compute using neurons one of these intermediate values that is, and then use that intermediate value as the error. So we've published on that and call that the prescribed error sensitivity rule. But conceptually, it is just the standard delta rule, which is the simplest neural network. It's simplest neural network learning rule. And then, of course, it's also possible to put lots of other ones in there. Okay, so that's how we tend to get E and D. That whole process, though, is relatively complicated. And it would be nice to have a software toolkit that would just do all of this for us. And we have such a toolkit. This is called Nengo. It's a Python package. You can download it off GitHub, and you can pip install it. And the idea here is you just simply specify those values and those and what functions you want computed, and it takes care of all these details for you. So what we're seeing right here now is a slightly sped up version. On the right-hand side is just the Python code that specifies the network that's being built. On the left-hand side, you have a live coding environment that as you type, you are getting the individual components being created. Each of those little sets of circles represents a variable that's being represented, and the group of neurons that is associated with that variable. And anytime you see one of those connection lines between one group and the next, you can specify a function that should be approximated, and you just simply specify that function in normal Python terms, and it will automatically use that function in order to find the connection weights for each of those components, and then connect all of those components up to run your final system. And you can see there that you can run the model from within the visualization interface, and see its behavior over time, because most of these networks involve temporal dynamics and behavior, and so you want to have some sort of way of interacting with it. Okay. Nengo itself is part of somewhat of a large ecosystem of tools. The core framework is just a Python package that's sitting here in the middle. That's just a Python package that is just uses NumPy, so it has very few dependencies. The graphical interface that you were seeing there, you were shown there, is sort of an optional graphical interface put on top of it, just using HTML. And then, importantly, the high-level description language of that model that you define your system in doesn't really specify exactly what neurons you're using or what hardware you're running on. And so that means from that one description, that one high-level description, we can then take that model and compile it for different backends. We can compile it for different types of hardware. You can either run it on the CPU or on the GPU, or on some custom neuromorphic hardware that's starting to be available. So, for instance, Spinnaker, a project out of University of Manchester. We can take all of those high-level models and just simply map them onto whatever that hardware is. And importantly, we're going to get slightly different networks depending on what we're mapping it onto, because different hardware may have different neurons. And so the actual connection weights may be different, but the high-level functional behavior is meant to be the same. In the middle of this diagram, or sorry, the bottom middle of this diagram, we're also noting our current project, which is let's make this work for FPGAs, because the whole system that we've sort of been describing here seems to fit very nicely into FPGAs. And so that's really what I want to talk about next. Is why these sorts of systems might be of interest for FPGA development. And then the goal would be that we can use this same software system, this Nengo software system, that gives you access to all of these things for defining networks, using deep learning, using backpropagation, using this sort of random least squared minimization approach for defining all of our networks. The software takes care of that behind the scenes. The only thing that the user is really focused on is defining their model, defining the behavior that they want using Python, using these just high-level aspects of like, okay, this is the vectors I want computed, these are the functions I want computed, and the differential equations I want. And then if we can run that on different backends, an FPGA might be an extremely efficient one. So that's what I'm going to talk about next.